Hi, it's me again. I figured we'd do another example with calibration. And so just in the name of letting the calibrations get as bizarre as we want, and still showing that, well, but it all works out. Like, you can get a pretty reasonable result no matter what. Um, the analysis doesn't need to be complicated, right? Why don't we do an example where we look at a data set and we want to try to do a fit that looks like this. I guess I don't really need a subscript there. This is a bizarre calibration. I'm not sure I've ever seen a sensor that uses quite this calibration. I have seen, and we'll talk actually in future lectures, I have seen measurement techniques where trig functions show up in the calibration, but this is a bizarre one. Okay, so let's do it. Let's create a little. Well, first let's derive the least squared analysis. Let's do the error analysis. So my error then will be defined as, this one's quite easy. No problem. All right, and then so the expected value of error squared is okay. And we're ready to start differentiating. So when we optimize with regard to A and B, remember this is a metric that tells us the total error. It's just a number, right? This is one number we can calculate from our entire data set, that for a given choice of A and B, these fit coefficients, these coefficients, these knobs we can turn as engineers. This is a metric that tells us just a number. It's a score that tells us how badly we did. We want to minimize it. We want to get it as small as we can. So we will play around with A and B until little tweaks of A and B no longer influence E. That's a sign that we've reached the bottom and we can't do any better. All right, so we'll know we're there when this is true, for example. So to differentiate this with respect to A, bring the 2 down. Don't touch the guts of the parentheses. And multiply by the inside derivative, which in this case, if I differentiate with respect to A, everything else that isn't A just looks like a constant. And I'm almost out of paper, but I made it. All right. Lovely. We can just distribute that cosine. Oh, and I can blow away the 2 because, you know, you can always divide 0 by 2. And here, now if I distribute the cosine, distribute my summation, here's what I'm going to get, that 0 is equal to I'm out of room. There. Or so this is what I get when I go through this analysis differentiating for A. you'll notice, and I'll let you do this yourselves, if you go through the same process differentiating for b, what you're going to get is this. There's a pattern here. Again, I'm doing this not because I'm a wizard. I'm doing this because there's a pattern, and once you see it, once you learn to see it after you've practiced this a few times, you can learn to trust your perception of that pattern. If not, you're just stuck doing it the long way. I'm not going to tell you what the pattern is. You got to figure it out yourself. All right, there you go. So you're going to end up with this as the expected value for when you repeat this by differentiating with respect to b. You get this as your system of equations. There we go. Lovely. All right, now let's look at a data set. So if I have an example data set, x, y. I'm only going to do a few data points. I don't want this to be tedious. So let's do about that. And then y is going to be, we'll say, oh, I don't know. Seems easy, right? I'm really making this up as I go. I honestly don't know what the answer is. All right, so when I look at my calibration, my optimization equations here, I see I need to calculate 2 multiples of y. So I need to add, well, let me start with x first, I'm sorry. So sine, I don't actually need to calculate the sine or cosine of x. I need to calculate cosine squared of x. I need to calculate sine x, cosine x. And I need to calculate sine squared of x. Now, fortunately, I happen to have chosen values of x that's going to make this really easy. I also need to calculate cosine y cosine x and y sine x. All right, and then I will have it. So here are my expected values. I don't need the expected value of x. It doesn't matter. The expected value, by the way, is going to wind up being pi halves. But we don't need it. Expected value x appears nowhere in these formulas. I don't need expected value for y either. I do need all of these expected values. All right, so the cosine of x of 0 is, well, 1. So you square that and you end up with 1. Cosine of pi halves, that's 0. You square that, you get 0. Cosine of pi is -1. You square that, and you get 1. All right. Now the sine of 0, it's actually this backwards. How interesting. Now the sine x cosine x is, in fact, at all of these points going to be 0. Isn't that interesting? Yeah. So think through it like this. Cosine of 0 is 1, but the sine of 0 is 0. At every single one of these points, either sine or cosine is 0, and I can prove that here, right? So this is 0 everywhere. It's almost like I chose those deliberately knowing that this was going to be a lot easier if I picked those. Without moving over here, we can already calculate expected values for these. So this is going to be 2/3. This is going to be 0. This is going to be 1/3. Nifty. All right, y times cosine x. So here we've got cosine of x is 1. So that's just 1. Cosine of x is 0. So this is 0. Cosine of x is -1. So this is -3. Interesting. All right, here we've got 0. Here we've got 2. And here we've got 0 again. Lovely. All right, this is going to be negative 2/3 is the expected value. And this one is going to be positive 2/3 is the expected value. There we go. We've got it. Okay. How to solve for this? So we've done our expected value table. We've got all of the expected values we need. Now we need a solution strategy. So we've got to solve for either A or B first. We are helped, and I'm going to go ahead and use this fact because I'd be crazy not to. Sine x, cosine x happens to be 0. I can work through the algebra to isolate A and B, but this is 0, and so is this. So what that means is, in our particular example, because I happen to give very, very friendly values, we know that A is equal to, I should make a note. Beautiful. There's A. And B. Let's see. B is going to wind up being let's see, so y sine x is 2/3. And sine squared of x was 1/3. So my fit is this. Let's see how I did. So if I plug in, let's see how well this actually matches the data. It's possible, especially because I was just making this up, right? It's possible that we actually do a very poor job of matching the data. No one said that we chose our function intelligently to match these data. In fact, these data form a straight line, right? Whereas this fit function does not. So let's see how we did. So this is what I get for our fit. So at x equals 0, 0 pi halves, and then pi. If I plug in for this, I get -1 here, and I get 0 here. -1, we're not off to a good start. And let's see, at pi halves, I get 0 here, and I get 2 here, right, because sine is 1. Okay, that did better. And then at pi, I get, this is going to be 1 and 0 again, so this is 1. Yeah, so not so great. We did not match the data very well, but apparently this is as well as we can do. All right, so, or at least that's what the analysis would have me believe. Okay, so there we go. That's working through an irritating example to show that, well, you can do this for just about anything. Thanks for watching.